Okay, so in this video, I'll show you how you can make a unipolar, or a different type of a fast slow leg PWM. So it basically means that one leg is slow leg and the other one is fast leg. So what that means is this leg switches with the frequency of the voltage that we want to generate on the inverter. And this one switches with the switching frequency that we want. So they have two different jobs. And I will show you how to implement it. And I've explained it in one of my earlier videos, so if you want a technical explanation of it, go ahead and watch that one. But let's get right into making this one. So I've already made the full bridge, because that is not important. I just haven't added the voltage source, so we can add the voltage measurement, so we can add that right away. So we have one measurement here, and then one measurement here. And then we can add a scope. Okay, and then we can make the control circuit. So you can see that it looks like this. So a nicer block diagram, you can find it in my course, where I have a block diagram here and also a mathematical explanation. So this is what the block diagram looks like. So the basic idea is that we want the slow leg to switch like this, so only once during one period of the voltage, and then the fast leg switches very fast. So this is just the duty cycle, so it switches a lot faster, and it should look like this. And this block diagram just decides the two gate signals based on the reference voltage that we want on the output of the inverter. So we can go ahead and make this one. So I think it's simplest to make the slow leg first. So that is just a comparator between the voltage reference and zero. So, we can go here. So we first can define a voltage reference. So that is just a sinusoidal signal. And I've already predefined a voltage reference, which is called Vref. And then we can just multiply it with the square root of 2. And then we also want to change the frequency. So the frequency is in rads, and this one is in hertz. So we want to multiply with 2 pi as well. So then we have the voltage reference. Then we can connect that to a relational operator in order to compare it to 0. We want to compare it with 0. So let's add a const and make that 0. So then we basically have the slow leg. So what you can see from the slow leg is that when the voltage is above 0, then the slow leg is 0. And when it's below 0, then we get 1 for the slow leg. So we can just add this directly into the slow leg. And then we want to make the fast leg. So here we want to first find the duty cycle. So if you look at here, you can see that it's basically this one divided by the input voltage, which is VDC. And then we add the slow leg as well. So then we can I just add a constant. But ideally, you should just measure this voltage. So then we have Vin is what I predefined, so it's 400. And then we need a divide block. So here we have normally the duty cycle, but then we want to change it so that we can use it here. So then we need a sum to add the slow leg. So there we have the duty cycle. So this should be the duty cycle, and this is the reference. I can just write that, Vref. And then we want to have a PWM, because now we have the duty cycle, right? So we have D, but we want the PWM. So then we need another relational operator. So we can just use what we had here. And then we want to compare it with a triangular waveform, which is a repeating sequence, I think. Yeah, here we can define a triangular waveform. So that is just how you make a quick PWM. So I have already defined a switching frequency. So after half a period of the switching frequency, we want a number, and then after one period. So after half a period, we want it to go up to 1. And after one period, we want to go back to 0 again. So then we get a triangular waveform. And this is basically the fast leg that we want. So if we try to run it now, it should work. Well, we can reduce this amount of time, and we also need a solver. So we can add a solver. I think it's called power or something. Yeah, there it is. And I want to change it to discrete time. I think that is better. And then just add 1 microsecond in step time. And let's see how it works. So So now it's finished, and then you can see that we get the behavior that we want. So if you imagine on average, it would be something like that, right? So then we can actually try to take the average of this to have a look. So I think we can add a moving average, and then add that into here. So we want a quite high frequency here. So let's say 2 times the switching frequency. So let's have a look now. Yeah, now you can see that we get more of a sinusoidal shape, but I think we should add another moving average. A double moving average would make it better. So this is not something that you would do like in the real world, but it is nice to use average filters to analyze what we have. So then you can see that it's even better. You can see it's more sinusoidal. Okay, so what you actually want to do is to add an LC filter. So we can do that really quickly here. So we can first add an inductor, and it's called RLC branch, I think. Yeah. So here we have a branch, and then we want to convert this into an inductor. So 1 millihenry is okay, and then connect it to the output of the fast leg. And then we want a capacitor as the then we want a capacitor, and I think this should be higher. So let's say 100 micro. And then we can connect this here. And in order for this filter to work, we need a load. So we can just duplicate this and make a load. So we have an LC filter with a load. So let's say, what is a nice value? Maybe 10. Now let's have a look again. So this actually shouldn't do anything to the voltage that we measured here. We should actually measure the voltage here. So I should add another measurement and then add a scope. So let's have a look how this looks now. So you can see that we now get more of a sinusoidal waveform with only this filter. So if you're tuning this filter even better, you can get better results. And also if you increase the switching frequency, you will also get better results. So I didn't really show you like the switching pattern here. So I think it would be reasonable to plot the slow leg and the duty cycle. I think those are the most interesting here. So we can try to plot those two. Then you can see that we get the same behavior as I showed you in the beginning. So in the course that I have, we get the same behavior. So the duty cycle starts off being sinusoidal, and then it jumps up because we add the slow leg. So then it get this waveform. So we get exactly the same thing here. So that is basically how we can make a fast slow leg PWM. And if you want to go deeper into how it works technically, you can go and watch my other video on that. And I also have a course, I actually have a course on PWM strategies that you can also try. So it's PWM strategies where I basically compare the bipolar PWM, the standard unipolar PWM, which is not this one, and then we have the fast slow leg PWM, which is this one right now. So they have their pros and cons for different things, and yeah, I think you should, if you're interested in like understanding the difference between the PWMs, I think you should have a look at this.